Let us consider a regular hexagon H in the two-dimensional plane. We divide H into 24 equilateral triangles, which are also congruent, by using edges which are parallel to its sides. For each of the 19 vertices of our small triangles, we assign 19 different numbers. Observe that in some of our triangles, the numbers in their vertices are arranged in a decreasing clockwise order. Every triangle which satisfies the last condition is called clockwise. This brings us to the main question in this challenge. We have the following main problem. Prove that the minimum possible number of clockwise triangles in our hexagon is exactly 7. Let us first prove that the number of clockwise triangles must be at least 7. For this, for every edge that we consider, which connects a number A and a smaller number B, we assign a directional arrow from the bigger number A to the number B. Now, we define the right and left sides of an arrow in the following way. If one walks in the direction of the arrow, then its right hand determines the right side, while its left hand determines the left side. We denote the right and left side of each arrow by the plus and minus signs, respectively. For example, if we take the following 4 small triangles and assign numbers to their vertices in the following way, then we will have the following signs in the edges. Observe that the exterior signs do not belong to the interior of any triangle. And thus, since we are only interested in signs inside our triangles, then from here and after, these exterior signs are excluded. For every shape, which consists of small triangles, we define its clock number to be the number of plus signs inside it, minus the number of minus signs. For example, the clock number of our current shape is equal to 0. Our main observation is that every clockwise triangle has 2 plus signs and 1 minus sign inside it, and thus it contributes 1 to the total clock number. However, if a triangle is not clockwise, then it has 2 minus signs and 1 plus sign inside it, and thus it contributes minus 1 to the total clock number. Hence, if our hexagon has k clockwise triangles, while the other 24 minus k triangles are not clockwise, then its clock number is equal to 2k minus 24. We can also obtain a lower bound for the clock number of our hexagon in the following way. For every choice of numbers in the vertices, which then leads to the arrangement of signs inside the hexagon H, we observe that the edges, which belong to 2 triangles, do not contribute to the total clock number. This follows immediately from the fact that such edges have 2 opposite signs from each side, which then cancel each other. Thus, the only edges that count are the ones which belong to only one triangle. In other words, these are the edges which are found on our hexagon H. Hence, in order to obtain the smallest clock number, we need that the minus sign will be attached to as many of these edges as possible. However, we also note that at least one of these edges will have the plus sign. This is because for the maximum number m of the vertices on the hexagon H, exactly one of the edges, which belong to m, will have the positive sign. This immediately implies that the clock number is at least equal to minus 10, Thus, we have the following inequality, which implies that the number k of clockwise triangles is at least 7. Now, all that is left is to give an example for a choice of numbers in the vertices of the triangles of our hexagon H, such that we will have exactly 7 clockwise triangles. We need to have as many minus signs as possible in the edges, which are on the hexagon H. And since there is at least one plus sign on these edges, we can get the maximum number of minus signs by the following choice of numbers. Now we can choose any different numbers for the rest of the vertices, and it can be easily seen that the clockwise triangles are the ones which are emphasized. Hence, we have exactly 7 clockwise triangles. This proves our main result, and thus our proof is finally complete.